Get started with class today. So, in terms of announcements, there really aren't any. Just do your homework, as usual. There's a midterm coming up. Someday we're going to write it. Before your midterm, we will schedule review sessions with Leticia and Mark. Inevitably, you guys are it's not gonna work for somebody's calendar, and for that, we apologize. And if that's your case, then your options are either move your calendar or come to office hours. Sorry. Beyond that, homework 3 is out. Has anybody downloaded it, just out of curiosity? Okay, well, that's a start. The next step is to start it. But we'll take what we can get. So it's nice to see everybody. Thank you for coming despite it being a grad student holiday, i.e. raining outside. It's nice to see you all and to continue our discussion of SVD. So the goal for today is to finish up with SVD, and in fact, to finish up with all of numerical linear algebra, which of course is a complete lie, because then like 4 lectures from now, we're going to come back to it. But we're going to wrap up with the SVD with one additional example of how to use this thing. Where we'll do a quick kind of recap of our story so far, and then move on to nonlinear problems. Namely, we will talk about root finding and Newton's method. We're a little behind schedule on the course schedule, and that's fine, because I made this course. So, like, whatever. Okay. So, as a reminder, in case you have been living under a rock or sleeping through the last couple lectures, essentially the object that we've been studying for a few lectures now is this sort of the final boss of matrix factorizations, known as the SVD, or singular value decomposition, which is U sigma V transpose. In the most generic version of this, U and V are square or orthogonal, and sigma is a diagonal matrix, which might be singular, and moreover, it's like this weird thing that's diagonal but not square. So like only elements I comma I can be non-zero, but it might be you have to pad one way or the other to account for the fact that U and V are square. And then we also talked briefly about how like you might slice off rows and columns of the U and the V to come up with this sort of economical version. Okay, so we've talked about a lot of applications of SVD. I think we've for example, justified some version of principal component analysis and approximating a matrix. The one final one that I thought we would discuss, which was my goal for last lecture, but we didn't get there, is something called the Procrustes problem, which hopefully you've all heard of because it was on your homework. If not, you'll learn how to do your homework. In particular, this is a problem of taking a generic matrix and approximating with an orthogonal one. And there's many different places where this problem comes up. We're going to talk about it in the context of a 3D computer vision style problem, but the reality is that this also comes up in high dimension as well. So it's one that's worth being aware of. So incidentally, has anybody ever heard, do you know where the name Procrustes problem comes from? It's worth reading because it's like totally weird, wild choice of names. So apparently Procrustes is like what, a Greek-Roman myth involving a guy that, how does this go? Like he has a bed in his house, and if you're too tall, he chops your feet off because you must fit in the bed, and there's no other solution to this problem. I don't know. There was no TikTok. It was a dark time. That was all they had. If you understand that story, let me know. But apparently somebody back in the day decided that was abstractly related to approximating a matrix with one whose singular values are all equal to 1. Your guess is as good as mine. And meanwhile, like I'm perfectly happy to see retribution for tall people. So the problem that we're going to talk about today is one that maybe is a little bit less violent, but I might argue is a little more practical, which has to do with alignment of point clouds. So in particular, the Procrustes problem is sort of the key step of a technique called iterative closest point, or ICP, not to be confused with the popular 90s band. And essentially the basic idea here is that you have 3D scans of some particular object. So for instance, this little 3-finger guy here. And very typically what will happen is you have a sensor, you walk around the 3D object and you catch it from different angles. And each time you do, you acquire what we call a point cloud, which is called a point cloud for obvious reasons. But the problem is that essentially as you move your camera around, the reference frame of the camera is changing, right? So you observe this point cloud, but it's like rigidly, if you're lucky, rigidly rotated from each other, or possibly translated in every step of your motion, right? And so this huge literature in computer graphics, vision, and other fields has to do with what feels like a pretty simple problem, which is called registration. So like you're given 2 views of a 3D object that are maybe displaced or rotated from one another, God forbid, flipped. And your goal is to put them all in a common coordinate system. So for example, maybe I scan this hand from all the different sides, and now I want to fuse them together into one dense point cloud. So the ICP algorithm kind of takes place in two steps. We're going to cover one of them and assume that a human does the other, which actually is a pretty reasonable thing. So let's say that I scan this point cloud from two different angles and I get the inputs like on the left. Here, these are borrowed from my textbook, which is why they're black and gray instead of more interesting colors. Moreover, you mark a few landmark points. So like, for instance, you look at the tip of the guy's middle finger and you mark that same point on these 2 point clouds. Right? So you have a bunch of pairs of points on these two things that should correspond to each other, but sadly, because these are in different coordinate frames, they're not aligned. And your goal is to bring them into alignment by optimizing for a rotation and a translation of the first guy into the second, or vice versa. Does that basic problem make sense? The ICP algorithm, by the way, it ping-pongs back and forth between that step and then updating the mapping. So like if somebody didn't mark those points that were matched to each other, then the way that ICP does it, which is sort of brain dead, is just use the closest point mapping. ICP as an algorithm has been replaced about 8,000 times in the geometry literature, so it's not worth covering in great detail. But this is sort of the key step of ICP and all of its derivatives, so it's worth mentioning. Notice it also showed up, for example, in your problem set for a very similar reason, which is you were trying to approximate the motion of your armadillo kind of locally as some rigid thing. Yes, Hamid? Sure. That's exactly right. So in fact, why don't we just flip to our next slide? So we have 2 point clouds. And now, ooh, yikes, that's a hazard. Man, okay. We have 2 point clouds, and here somebody has marked pairs of points that we think should correspond to one another. And we think, moreover, that there is a rigid motion that takes me from one to the other. So here I've got point cloud 1, so this is indexed x1i, right? And you can think of these as like vectors in R3, probably. And then x2i, which is the points in the second point cloud. So this is like hand 1, hand 2. And my optimization variables, there's actually 2 of them in this problem. One is a 3 by 3 matrix R, which is like the rotation, and then a translation vector T that says I take every point in x1, I rotate it by R, and I translate it by T, and then I want to end up on x2. So in particular, the sort of conceit of this algorithm is that I think R times x, what notation did I use? 1i, or I1, 1, whatever, plus T is equal to x2i, like that, roughly, right? So this is an approximation because our point clouds are noisy. And so our optimization variables in this case are not the x's, it's the r and the t, right? So like the problem on the screen is kind of a weird slick notation, so let's convince ourselves that this is the same. So in particular, this is, we want to be true for all I. So as is sort of our generic formula in this class, what do? We subtract the 2, square, and try to minimize, right? So here, I'm going to define a new matrix, which is x1, which is just like the first vector, the second vector, third vector, and so on, right? And similarly for x2, right? So if I want to apply a rotation to all of our x's in one shot, which is hopefully something that you guys are getting used to. Like for example, in your previous homework, a lot of people in office hours thought through how to like kind of vectorize their mathematics. So like you have some for loop over I. How do you write that in terms of matrix vector product or matrix product? So in this case, rotating all of the Rx, all of the individual xi's here is the same as just pre-multiplying this X matrix by R. But now notice that like what I really want is I need to translate each of these guys by the same T, right? So in principle, what I kind of want is like this, where I just take T and copy it a bunch of times. Does that make sense? And if you think about it, this is exactly Rx1 plus the vector T times the vector of all ones transpose. So this is just fancy notation. And if you kind of check on your scratch paper, what you can convince yourself is this is the matrix whose columns are just copies of T over and over again. Okay? And so that's what you see on the screen, right? So the first term here is the rotated and translated vector, wrong class, point cloud x1. And then the second one is point cloud x2. And now we subtract the 2 and we want them to match. And our variable is the rotation and the translation. By the way, I keep saying rotation. R could also flip, right? So for now, we're considering orthogonal matrices. Does that answer your question? Yeah, so that's a slightly different problem. So that's called partial registration. Here, we're assuming that you see maybe the whole point cloud in each view, but they're still rotated and translated from one another. Yeah, it's absolutely the case that if you only see partially, so for example, I point the camera at the hand this way and that way, I see different points, then the sort of simplest thing you can do is just figure out which points are in common and then apply this algorithm. Yeah. Incidentally, if you want to see this thing in action, I got really excited about this the other day. I had to get a retainer at the dentist. And it used to be, in my day, they made these little wire torture devices. But these days, they actually put a 3D scanner in your mouth. It's super cool. And they'll have this person like sit there and wave around a point cloud scanner of your individual teeth. And you can watch on their computer screen as it solves this registration problem live. Like your teeth are actually moving around and registering to one another. I was very excited about this. And then they 3D print it. Apparently, my PhD advisor got a lot of money from the early patent on this stuff. Okay, so we want to solve this optimization problem. We have two different variables. What are we to do? So the first thing we're going to do is we're going to start with our objective function, like what's on the screen here. Why is it like flashing? Oh, it's, wow, I managed to slash the HDMI cable by knocking on this thing. All right, well, we're going to hope that that stays in one piece. Yikes. Oh boy, I gotta stop eating so much. All right. Right. So we're gonna simplify our objective function here, and then we're gonna optimize. And our strategy is gonna be a little sneaky. We're first gonna find a formula for t, because notice that that kind of looks like if I froze r, the optimization for t kind of just looks like least squares. So like this is gonna look, guess what? Like exactly the same optimization problem we solved about 5 billion times so far in this class. Then we're going to plug that back in. Now it becomes purely a problem for R, and then we're going to do the non-trivial stuff. Okay? That's our strategy. Okay, so let's start our objective. Sorry, let's start our math here by optimizing with respect to t. In particular, today we're going to start using some mathematical identities that are really important for lazy mathematicians in numerical analysis, and they're ones that you guys should get used to using. It's the kind of thing that you never actually need. Like you can always prove with like all kinds of weird summation identities, or you can remember just a few useful fun facts that make least squares problems much, much easier. In particular, one thing you might recall from your first chapter of the textbook is that the Frobenius norm can be written as the trace of A transpose. If you don't remember this fact, you should double check it on scrap paper. It's just like index math. And the other thing is that assuming the dimensions work out, namely that you need a square matrix in order to take its trace, then the trace of A times B equals the trace of B times A. Okay, now these identities seem simple, but they're actually very useful shortcuts for doing a lot of mathematical proofs. Like you can kind of see already what's going to happen. Like we have a Frobenius norm in our expression here. We're going to simplify it by using this kind of thing and then like cycling traces around. Yeah. So in general, when you have like least squares looking problems, I would strongly suggest plugging this kind of stuff in as like a very efficient way to do mathematical proof. And since we're all grown-ups here, it's time. No more index math. Okay, so let's start with our objective function and see if we can simplify it using these identities. So first of all, this is going to get a little ugly, so we're going to do part of it, and then I'm going to do the thing that I used to hate when professors did, which is do like a ... trust me, and the final formula, because I'm lazy and we need to get forward in this class. But I'll get you the idea of how to do this kind of derivation. So what is our objective function? Well, we've got this expression here inside of a Frobenius norm. So in particular, this is r x1 plus t times the vector of all ones transpose minus x2, that whole thing times its transpose. Everybody with me so far? So far, this is horrifying, yeah? Okay. So what we're going to do, well, the first thing we need to do is actually take the transpose of this thing and then just multiply out a giant product. I'm so sorry. We can do it. Okay? So in particular, what is this thing? Well, the first term remains the same, rx1 plus t1 transpose minus x2. Now we have x1 transpose r transpose. As in my office hours, this was a common mistake. When you take the transpose of a product, they flip order. Plus 1t transpose minus x2 transpose. This is not in my notes, so if I make a mistake, you should catch it. All right, and now we got to do a giant product. So here's the good news. Let's think about, for example, the very first term in this product. We have Rx1 times x1 transpose times R transpose. Yeah? Let's just think about that for a second. So we have trace of Rx1, x1 transpose, R transpose. Now here is where these little identities are going to be really nice for us. Because remember, essentially what this identity is saying is if I have a long chain of products like this, I can kind of just cycle them around. You see that? So in particular, I can take this R transpose and I can put it there, right? Because trace of AB is a trace of BA. Now in our optimization problem, what is R transpose R? There you go, you guys are speaking up now. This is great. By the end of this course, you could be like yelling, which is what I'm looking for. So in particular, now it vanishes altogether, right? So notice that already we're simplifying our problem because that's become a constant with respect to our unknown variable. You see the kind of strategy we're going to do a lot here? Okay. Here's the part where I'm going to write a big expression and I'm going to ask you to like not trust me, to think critically, but I'm going to write it first and then we're going to kind of eyeball and make sure I didn't make a mistake because making that argument for every pair of terms here is going to be kind of a headache. Okay? So in particular, oh no, I erased it. Oh no. Okay. Technology, like I used to use paper. Okay. Right, so we're going to get the trace of x1, x1 transpose. That's what we just showed. Plus, now if we pair the last two terms together, we're going to get x2, x2 transpose. That part's okay. We'll get those out of the way first. Now, we're going to start thinking about cross terms. So next up, we've got 2 times r x1 minus x2, all that times 1t transpose, like that. We've got a minus 2 r x1 x2 transpose. I'm going to justify this in a second, I promise. Plus nt t transpose. Okay. So let's go through our different terms and make sure that you believe me. Yes? N is, good question, the number of points in our data set. So let's think about what happens. In particular, let's look at the product of this term and this term, right? So you have T, 1 transpose, 1 T transpose. What is 1 transpose 1? It's the dot product of the vector of all 1s with itself. So what is that? That's 1 plus 1 plus 1 plus 1 dot 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 plus 1. Yeah? N times. So that's where this factor of n comes from. Good question. And what are our other cross terms? So for example, here you have R x1 minus x2 times 1 transpose and so on. Does everybody believe this formula? Cool. All right. So this is about as good as we can do. The good news is that we've isolated some terms that are going to affect our optimization problem, right? Like specifically, these first two terms here don't have an R or a T in them, right? And this whole thing is a giant sum, so that it's linear. So notice that those first two terms don't affect our objective. That's kind of nice. Yeah? And moreover, okay, so this term doesn't have a t in it, so that's kind of nice. This one just looks like t squared. Quick sanity check. What's the gradient of the trace of nt t transpose? Can we do this in our head? Oh, it got so quiet suddenly. Okay, let's think about it for a second. The trace of t transpose, that feels like a complicated thing, but we basically are programmed to just do one thing over and over again, right? Which is to cycle traces around. Notice that this is the same as the trace of t transpose t, yeah? Now, what is this object? So this is a 1-by-1 matrix, right? This is an expression we've written so many times in this class. What is it? Yes? Yeah, this is just the norm of t squared, right? So now it's pretty clear our gradient is just 2t, yeah? I guess with an n factor in front of it. Okay? So this stuff isn't scary. Notice it's just an efficient way to derive formulas. Yeah, that's all. And basically, sometimes it's more convenient to work with matrices. Sometimes it's more convenient to like cycle things around and work with scalars. Cool? All right. So when we take the gradient, what we're going to find, this is the gradient with respect to t of our objective function. Okay. Well, we basically have two terms here, right? One is this guy, and 1 is that guy, if we're optimizing with respect to t. Yeah? Okay. So this one we already know is going to lead us to 2n times t, right? That's the gradient there. What's going on here? Well, remember, I can cycle the trace around. This is really the trace. The trace of this expression is the same as the dot product between t and this vector. Do you see that? So it's actually just linear. So that's kind of nice. So at the end of the day, the gradient is going to be 2 times rx1 minus x2 times the vector of all ones plus 2n t. Does everybody believe me? Do you see what happened here? This is a linear expression in t. It's the dot product between t and this ugly thing after I cycle the trace around. And the derivative of a linear thing is just the coefficient. So that's this term. And this is the one that we derived before. Cool? Well, this is fabulous. Do you see this? Because we just derived a formula for t. Yeah? So in particular, we set these things equal to one another. So what we learned is that t is equal to 1 over n x2 minus r x1 times the vector of all ones. Now, we did a bunch of algebra, and it's easy to get lost and think of this as just some weird abstract expression that I like very dutifully type into Python. But let's think for a minute. What is this expression? What does this tell us about life? What is the optimal t? This is one of these things that in retrospect you should have been able to guess. Yes? Yeah. So think about this. So remember that like multiplying by all ones is the same as summing up all the columns. Yeah. So x2 times the vector of all ones divided by n. What is that? That's the center of mass of x2. Yeah. Similarly, x1 times the vector of all ones, the center of mass of x1. I rotate it. And now, essentially what we're saying is that the translation is just the thing that brings the centers of masses of those two things together, which is kind of what you would expect. Cool? It's important to sanity check these little formulas. I think it's easy to get totally lost in a bunch of symbols, but the reality, this is a very concrete geometric thing that we're doing. Okay, so so there's our formula for t, and now we're going to do something horrifying. I'm so sorry. We are going to plug this formula for t back into our objective function. Notice that it's like kind of nice. It's just linear in r, or affine, I suppose. And now we have an optimization problem just for r, right? We can eliminate t. Did you have a question or just itch? Okay. So, which is allowed. Okay. Right. So like maybe we call our objective function E for energy. So now, notice that basically what is this doing? It's saying if I know r, then I know t. I can think of r as a function of t. Or the other way around, t is a function of r. So what we're going to do is we're going to take our objective function, we're going to write it just as a function of r, assuming t is optimal. Right? We can certainly do that. What are we going to get? Well, now it's ugly. Oh my gosh, I'm so sorry. This is so yucky. Okay, so we're going to get r x1 plus t times the vector of all ones transpose. So now we have a 1 over n times x2 minus r x1, like that, times 1, right? That's this expression here, times 1 transpose, minus x2 Frobenius norm squared. I see some furrowed eyebrows. You see that I just took the objective function at the top of the slide and I plugged in our expression for t, and then I probably made a mistake somewhere copying. That's maybe why you guys suddenly look confused. I rely on your eyebrows as my like correctness, my like compiler as I teach. Okay. So here's the part where I'm going to ask you guys to trust me just the tiniest bit. So let's say that I go through exactly the same argument we had on the previous slide. I write this as a trace, I cycle things around. Hopefully you all believe me that one could do such a thing. Then essentially the expression that I'm going to get is going to be as follows. It'll be some constant. Here when I say constant, I mean there's no r dependence. Minus 2 times the trace of r times some big ugly thing. x1, x2 transpose minus 1 over n times x1, 1, 1, transpose x2 transpose. Is everybody okay with trusting this little step of the proof? It is exactly the same algebra as on the top board. I'm just now applying it to a slightly different expression. Okay. Here's the good news. I can be totally lazy. This is some weird matrix, but at the end of the day, it's written in terms of the inputs to my problem, right? So like I can clearly compute this object. So in particular, let's give it a name because it's ugly and we don't want to look at it. So let's call it C. Okay, so now our problem looks pretty nice. It's a constant minus 2 times the trace of our C. See, now it's fun, yeah? And the good news is, like, if I'm coding up an algorithm, it's perfectly fine to have C equals this thing. Like, that's no big deal, yeah? Okay. So why would I do that? Well, remember that our job is to minimize E of R, and I've simplified, and now I can say that, well, that's the same as maximizing the trace of R times C. Cool, so now our problem is starting to look kind of nice. Of RC, subject to the constraint R transpose R is the identity. You see the strategy here? This is like a good strategy in life. Like take your problem, cycle traces around. Anytime there's something ugly, just give it a new name and then forget about it. And see how simple you can make your problem. Okay, so let's think about this optimization problem. And essentially all that remains is to show how to solve this thing, right? Because then in code, what could I do? Well, I could code up this C matrix, solve this problem, and then the formula there gives me a formula for T. Does that make sense? That was a lot of words. Did that parse? So what remains is to solve this thing. This is the optimization problem called the Procrustes problem. Essentially, this is saying I want to take C and approximate it with R as closely as possible with the constraint that R has orthonormal columns. Yes, me. There's an argument about C being positive definite. Absolutely not. Ah, so in fact that is not needed. You were right for least squares problems. In this particular case, if you want to be fancy mathematician about it, this is a compact set. So there's no need for boundedness in this case because my constraints make me on a sphere. Yeah. So this actually works regardless of the sign of the problem, which is good because our matrices could be indefinite. Yeah. Any other questions? Okay, so what remains is to solve this problem. Any ideas for what we're going to do? Like probably like given the topic of the last 2.5 lectures? Yes. Oh, cool. Yeah, so basically, to distill our answer a tiny bit, we should probably use the SVD somewhere. I mean, there's a lecture on SVD, yeah? And this seems like a good place to do it. In general, again, in life, anytime we have an ugly matrix, we give it a new name and we ignore it. Anytime we have a linear algebra problem we don't know what to do with, we use the SVD. So, in particular, let's factor. And notice it's perfectly fine in our algorithm for solving this rigid alignment problem to call this a step. C equals U sigma V transpose, like that. Okay? So what am I to do? Well, all right, so let's think for a second. Let's now plug that back into our objective function. And remember, like essentially we just have two strategies. One is cycling traces around, the other is computing SVDs, and we're just gonna keep doing them over and over again. So notice that the trace of R times C is equal to the trace of R U sigma V transpose. And by cycling things around, this is the same as the trace of V transpose RU times sigma. Yeah? Now here's a kind of sneaky thing. R is orthogonal. By definition of SVD, U and V are orthogonal. They're also just constants in terms of the inputs of my problem. Yeah? So here's a kind of fun thing I can do. Let's just give this matrix a name. Any suggestions? How about R squiggle? Before one of you guys yells out like George. Okay. Notice that if I know R squiggle, I know R. If I know R, I know R squiggle. Because like U and V are just constants. So in particular, now my objective function is even simpler. It is the trace of R squiggle times sigma. And sigma is a diagonal matrix. Do you see what I'm doing to this problem? I just keep stripping away structure until it's as simple as possible. Okay? All right. Notice that R squiggle is orthogonal just like R, right? Because I've post multiplied by orthogonal matrix. Okay. Now we're almost done. Now the temptation which is a serious temptation. I understand the urge, especially given previous lectures in this course, would be to say, aha, I have a constrained optimization problem, I should use Lagrange multipliers. And you absolutely can do that. For this particular problem, it turns out there's a clever argument that saves you a bunch of time and doesn't require Lagrange multipliers. So let's do that instead. So our optimization problem looks like we want to maximize, if I recall, the trace of R tilde sigma subject to the constraint R tilde transpose R tilde is equal to identity. And notice that our objective function now is really simple because sigma is just weighting the columns of R tilde, right? So this is really the sum of sigma I times R tilde I. Does that make sense? Okay, so let's think about rotation matrices and orthogonal matrices for a minute. Yeah? So what do we know? Like, kind of by definition, we know that all of the columns have norm 1, right? Let's say that I have a vector, and its norm, its 2 norm, to be precise, is 1. Can that vector have an entry that's 7? No, right? Like, because remember, it's the square root of the sum of the squares. In particular, if I take any one of those terms, then it becomes like the absolute value of that one guy, right? So in particular, what do I know about R tilde II? Yeah, it's less than or equal to 1. Moreover, I know that the sigma i's, by definition, are greater than or equal to 0. So if I can find an R tilde where Rii is equal to 1, then I know I can't do any better. Do we have any suggestions? So what is an orthogonal matrix whose diagonal elements are equal to 1? It's not a trick question. Yes. The identity. That's exactly right. So what we can conclude is that. Ta-da! So basically, we took our problem and we just kept reshaping it and reshaping it and reshaping it until it became so trivial the solution of the identity matrix. Now we have to be a little bit careful. We need to unravel all the lazy math that we did to read off a solution. Notice, so we have R is equal to V transpose RU, or rather, R tilde is. So in particular, R is equal to V R tilde U transpose. And now we know this is V U transpose. And now this gives us an algorithm for solving the rigid alignment problem. Do you see that? So you construct that matrix C, which we just defined up there in terms of, I think, no, we defined it, here, in terms of the inputs to our problem. So that's perfectly fine. Take the SVD of C, and now we just have a formula for R, which is VU transpose, and moreover, we already derived a formula for T in terms of R, and so we're all done. Yeah? Isn't that cool? Incidentally, the first edition of my textbook is completely wrong, so you shouldn't look there. You should look at the version that's in the course notes. I don't know what I was thinking when I wrote it. In particular, the formula for T is just like wild in that one. Call it a useful indiscretion. All right, any questions about that? So now we can do rigid alignment. Yes? Oh, sure, yeah. So the question was, why is this value less than or equal to 1? So remember that R tilde, the columns of R tilde are unit vectors, right, by definition. A unit vector can never have any entry that is bigger than 1. Because if it did, the norm of that vector would be bigger than 1, right? So if we want to maximize this expression, the best we can do is to put a 1 there. And in particular, the identity should go there. Something that we have not argued is that that is the only solution, right? So that's something worth thinking about. The short answer is like it is, but you should think about it. Yes, me. Yep. Nope. All matrices have positive singular values. Don't look so disappointed. No, and in fact, well, I think you're basically right that C might be positive definite. Notice that I have subtracted something here, so it's not obvious from this expression. Yeah. It also is not clear why you would want or care for this to be positive. It's like some kind of covariance matrix, I guess, but It's important not to think too hard. Like we derived a very simple formula here, so I think we're good. Okay, so with that, we have actually concluded our discussion of SVD. The textbook actually contains one additional problem, but we're already behind, so we're going to skip it, which is just, remember our original motivating example for eigenvalue problem was basically PCA. One thing that's worth noting is that a small extension of the Eckert-Young theorem that we derived in our last class shows that if we want more than one PCA axis, we can get it by just computing more than one singular vector. Basically, our original proof showed that the principal singular vector is the principal PCA axis. But if you apply the theorem we had last time, which showed that like SVD gives a good approximation of a matrix in rank K, then essentially what that justifies is the more generic version of PCA that we all know and love. So I will let you guys read about that at home. One kind of fun application of this is to like do this on a big set of images of faces. This is this very old school computer vision algorithm called eigenfaces, which is actually a pretty reasonable basis for a data set. So with that, I am pleased to share with you all that we are officially done with numerical linear algebra. So we're going to spend just a few minutes summarizing our story so far. I'm about an hour late lecture-wise from where I wanted to be at this point in this course, but that's okay. And then we will begin our exploration of nonlinear problems by talking about root finding. Okay. The good news is, even if like you might have gotten lost a little bit in all these nasty proofs and indices, you should like get back on board because these algorithms are going to be simple and it's a bit of a reset. Okay, for like a lecture, and then it's going to get ugly again because we're going to talk about the Broyden and BFGS algorithms, and those are kind of ugly to derive. Okay. So in particular, so far, basically we've had two little segments in this course. One was just a generic introduction to numerical analysis. We talked about condition numbers, that kind of thing. And then we spent the last many weeks basically solving two problems, AX equals B and AX equals lambda X. Hopefully we all know that. And we've talked about many different algorithms along the way. Since your midterm is coming up, and just to kind of put a bow on what we've done so far, I thought I'd just give you a quick reminder of our story so far so that we're all on the same page. Essentially, remember that we talked first about algorithm for solving AX equals B, called Gaussian elimination. And as a quick recall, that was nothing more than just codifying what you probably would do by hand to solve a linear system of equations in a way that a computer could use, right? And this took place in two phases, one that was forward substitution and the other was back substitution, which possibly may need pivoting, right? If you do not use pivoting, then the Gaussian elimination can fail. It can just end up dividing by 0. And essentially, we introduced this idea of an elimination matrix, which is just like a weird way to remember all of those steps. This is not to say that these are matrices you should compute, but rather just a convenience for deriving what we call the LU factorization. This thing is a cubic time thing to compute, which basically is just caching the steps of Gaussian elimination. And the good news is once you have done that, then solving AX equals B takes quadratic time instead of cubic. What's the gotcha? Well, the gotcha is computing the LU factorization itself takes cubic time, right? So like there's sort of a conservation of cubicness. If I ask you, does every matrix admit an LU factorization? Every square matrix, maybe. The answer is no, for exactly the same reason as the previous slide, right? That like, remember that Gaussian elimination just remembers, or rather LU just remembers steps of Gaussian elimination. In particular, if you need pivoting, then you need to introduce a permutation matrix. For example, PLU or LUP. Both of those are actually okay. All right. From there, we looked at structured problems and noticed that most of the linear systems that we encountered so far were actually secretly least squares problems, and that led us to a different matrix factorization called Cholesky, which relied on having a symmetric and positive definite matrix. This improves the storage and actually is a constant factor faster to compute, and it preserves some structure, which we're going to find is nicer later in this course. We haven't really used that fact yet. From there, we move to a slightly different set of problems, like understanding the span of the columns of a matrix, right? And that led us to QR factorization. There are actually 3 different algorithms we covered, or at least 2 in class, and one that's just kind of mentioned, which is fine. Obviously, I'm not expecting you to regurgitate the third, which were the Gram-Schmidt algorithm and Householder, both of which are just different ways to orthogonalize a set of columns. Right, if you recall, Gram-Schmidt kind of takes a matrix and post-multiplies it a bunch of times to orthogonalize the columns, whereas Householder pre-multiplies by a bunch of orthogonal matrices to get an upper triangular thing. That's the way to kind of remember the difference. And the good news is that that allowed us to solve the least squares problem without squaring the condition number, which was sort of our goal to start out with there. Yeah. Moreover, there are some applications we'll see later where you only need Q or R, but not both, um, which is kind of fun. Okay. From there, we talked about eigenvalue problems, right? So the basic kind of generic version of the eigenvalue problem that we're concerned with in this class is where your matrices are diagonalizable, meaning that you have a full set of eigenvalues. And the key theorem that we used to justify that was the spectral theorem, which basically says if your matrix is real and symmetric, or if your matrix is Hermitian, which is sort of the complex version of symmetric, then you got a full set of orthogonal eigenvectors. And the good news is actually computing eigenvectors at the end of the day is very straightforward. It's just multiplying by a matrix a bunch of times. Right? That's basically all we did. Like all of our algorithms were just like cute coats around that basic observation. And then finally, in our last couple lectures, we derived SVD. So what are the sort of themes that we should extract from this story so far? I think in general, so numerical linear algebra could be the topic of a year-long course. There are so many algorithms out there, and essentially we have just scratched the surface. I think the way to think about what happens next in terms of advanced topics is that essentially what we've begun to notice is that our matrices have different structures, right? Like maybe they're sparse, maybe they're positive definite, maybe they're symmetric. And essentially what we've done in this course is derived algorithms that work for all matrices, but that doesn't necessarily mean they're the fastest or the most space efficient for any particular matrix, right? And so essentially there are so many different structures that you could look for in a matrix that might suggest more specialized algorithms. So for example, in your homework, you derived, I hope, an algorithm for LU factorization of a tridiagonal matrix, which is a matrix who just has stripes down the middle. And hopefully you notice that that algorithm ran in like linear time, which is way better than any of the things that we did in class, but it put a very strong assumption on the structure of your matrix. So on this slide, I have included, at least off the top of my head, a long list of very typical structures you might find in numerical problems. The other thing that's worth noting is that this class is called Numerical Algorithms. And one thing you probably have figured out by now is that on your homework and what we do in class, there's sort of a weird mismatch. Do you see that? That we spend a lot of time in class deriving algorithms for things like solving AX equals B, doing eigenvalue problem, whatever. But my general life advice to 98% of the students in this classroom is you should never implement any of these algorithms, right? That the reality is that the key skill in numerical methods is to figure out how to call someone else's code to solve each of these problems. Now, it's important to understand what's going on behind the scenes because as you've seen, for example, in the last homework, I think many of you guys noticed in my office hours that the linear solver, if you code it wrong, can fail in some weird ways. And interpreting the error message, interacting with these tools properly and so on requires at least an intuition for what these algorithms are doing. But the reality is that there are blazingly fast and extremely reliable implementations of everything we've talked about so far. So the key skill that I really want our students to get out of this course is a little bit of understanding of the numerical algorithms. The reality is underneath each of the ones we've covered is a giant literature of ways to make them faster and stabler. But more importantly, an intuition for oh, here's this new problem I've encountered in my application in machine learning, graphics, whatever. If I munge it around enough and I play with my terms and I cycle traces and do whatever, eventually I can reduce it to just calling one of these pieces of code. Right? And so far, most of your homework problems, for example, fall into that. And of course, the other question that you can ask when you solve these kinds of things is about conditioning, which is essentially how do you expect any numerical algorithm to behave on a problem that you've encountered? Right? So we've talked about it generically, but of course you could take a problem like rigid alignment, look at the matrix C, for example, that we derived here, and ask is this a well-conditioned matrix for eigenvalue problem? Maybe it is, maybe it's not. No? Okay. That concludes part 1, well, 2, I guess, of this class, numerical linear algebra. So today we're going to get a jump start on the next part of the course. I saw somebody getting up. Sorry, it's still 40 minutes. Where we're gonna talk about nonlinear problems, and in particular, we're going to talk first about root finding, so solving problems f of x equals 0 for x. Then we're going to talk about optimization. Now, the vast majority of optimization algorithms actually basically look like root finding algorithms, right? Because one way to minimize a function is to set its gradient equal to 0, which if you think about it, is some equivalence. Equivalence is the wrong word, but some reduction of optimization to root finding. We're going to spend a lot of time on different optimization algorithms. We'll cover constrained, unconstrained, gradient descent, some kind of iterative quadratic things. my goal is to introduce some algorithms that are very popular in machine learning world, like gradient descent, stochastic gradient descent, and also to introduce some algorithms that are very unpopular in machine learning world. Because the reality is that like many of you guys as engineers will encounter problems that have relatively small numbers of variables or data sets, and then SGD is not the solution to your problem. And so we'll talk about some more classical techniques that can converge really quickly in that regime. Okay. And then finally, we'll probably conclude this class with integration and differentiation. So like solving differential equations. So that's sort of our preview so far. So with that, we're going to move on to nonlinear systems of equations. Any questions? I should pause for a minute. I'm talking too much. Y'all are so quiet. Cool. And while I wait for you to formulate your questions, I'm going to flip to my next set of notes. Oops, not that one. Okay, so let's talk about root finding. And the good news is that these algorithms, I think, are relatively easy for now. So what is our goal in root finding? Well, it's a relatively straightforward problem. It's basically, oh, I see. To solve problems, f of x equals 0 for x. Yes? Oh, I'm sorry. I forgot to post these slides. I will do that at the very end of class. Don't let me forget. The good news is you'll be able to follow along. This is simple for today. Okay. So basically, part 3 of this course, the main takeaway that you should encounter is that, like, okay, many problems can be solved with numpy.linealg.solve, but not all of them. And in particular, there are some problems that just aren't numerical linear algebra problems, that have nonlinearities. There's nothing we can do about it. In fact, I should note that we actually already tackled a nonlinear problem in this class. So if the definition of a linear problem is one that can be solved with ax equals b, then notice that actually eigenvalue problems don't fall into that category. This is partially just like a semantic thing, so like you shouldn't worry about it a lot. But the eigenvalue problem is absolutely nonlinear. Here's a way to see that. So like, let's say that I write our favorite expression, ax equals lambda x. Right? We can all hopefully agree that this is the basic problem we try to solve. Notice, what are our unknowns in this problem? It's x and lambda. Yeah? And if you look in this expression, there's a product of those two things. So this is very much not a linear problem. This is quadratic. One fun question, by the way, you should think about is like, what about like cubic problems in degree 5? I claim that all problems are basically either linear or quadratic. So there's a fun way you can do that, which is exchange dimensionality for degree. So like, for instance, let's say that I have some optimization problem involving x cubed. One thing that I could do would be to say, well, that's also x squared. Maybe that's, x times y, where y is equal to x times z, where z is equal to, right? So you see that you can basically sort of introduce inconvenience variables to reduce degree of your polynomial. That's not going to matter a whole lot in this class. If you take a class from my colleague Pablo Perillo, who's an expert in sum of squares hierarchies and all these magical algorithms, then this is the basic trick that gets used a lot in that universe. Wrapped around by like fancy things in algebraic geometry that I'm afraid of. Okay. So our more generic problem that we're going to try and tackle in today's lecture, and probably the next one or two, is a root finding problem, which in its most generic form says I'm given some function f, and my job is to find a point x star where f of x star is equal to 0. Now, as I pose the problem here, does this feel particularly solvable? So first of all, the one question you might ask is, what does it mean to be given a function? I think in this course, what that means is you're given like literally a piece of code where I stick in x, and what comes out is f of x. And let's say that's the only thing. Like I give you a piece of software and I say, my software takes like a little function pointer to f and it gives you back x star. And it makes no assumption on f. Do I expect that software to do particularly well? No, I think for like any number of reasons. So for one thing, I've put no constraint on x. X could be anywhere in like the whole like Rn, right? So for all I know, like I'm solving my root finding problem in 1D, whatever, I find this point here, and then like 5,000 miles somewhere over there is a point, which is like another root, and I just never think to look there, right? Because all I can do is put in an x and see if I got a 0 or not, right? So first of all, this problem doesn't feel well posed from that perspective. Moreover, there are f of x where you clearly shouldn't have any business solving the root finding problem. So for example, here's one that I think we can all agree, where root finding is not even well posed. So here f is equal to -1 when x is negative and 1 where x is positive. You could debate and say there's a root at x equals 0, but I would say this has no root because, well, there's no x where f is 0, yeah? I mean, this feels like a goofy example, but this is just to say that this is not a generic problem you expect to be able to solve numerically. You need some assumption on f, right? Of course, if you want to be even worse, maybe you'd like do one of these crazy things, right? Real analysis is full of examples like this. So basically, my point is what? That like, if you want to solve root finding problem, what's very typical is to write an algorithm or a piece of code and say, my code works for f so long as f satisfies some condition. Yeah? And so like, what are typical conditions for root finding? One is just continuity, which so the previous two examples do not satisfy. Notice that continuity is already super useful for root finding. Like, for example, in one dimension, if I find a point here and a point there with a positive and negative value, I know somewhere between those two locations is a root, which can be enough to justify our first algorithm. But there's actually nicer structures that we're going to use in this class that are going to allow us to derive algorithms that converge even more quickly. So for example, one of the ones that I think is used a lot in this literature is something called Lipschitz continuous. Now, this expression might not feel familiar, but I think if you take this expression on the slide and you divide both sides by the norm of x minus y, let's assume x is not equal to y. Notice what this is saying. Like, if I take x and y approaching one another, right, this is like f of x minus y divided by the distance between x minus y. So this is kind of like a bound on slope. Do you see that? And in fact, under some weak conditions, those two things are sort of equivalent. So basically, a Lipschitz function is one that satisfies this particular bound for any pair of x and y, meaning that basically the growth rate of my function is upper bounded by c. We're going to find in this particular case, if c is less than 1, we can solve root finding even more efficiently, which is kind of cool. And that's what we use to justify Newton's algorithm for differentiable stuff, which, by the way, is another assumption that we often put on our functions. Okay. And in fact, the more generic version of differentiable is this funny notation like c upper script k, which is basically saying that I have k derivatives that exist for my function and all of them are continuous. This one we're probably not going to use a whole lot in this course, but there are algorithms that like compute your function Taylor series up to term 5 or whatever, and then try to do root finding on that and then iterate, right? And so you could imagine some techniques that need this kind of assumption. Okay, so I don't think I'm saying anything too unreasonable. The good news is we have gone into the forest, done really nasty SVD calculations. Now we're coming back out and doing simple stuff for a little while. Okay. So for today's lecture, and I'm guessing maybe a little bit of the next one, we're going to start by solving one-dimensional root finding. The good news is these problems are pretty straightforward. The main theoretical result that you guys should all be using for one-dimensional root finding problems is a result that you all know intuitively, but you might have forgotten from high school calculus, called the intermediate value theorem, which is one of these ones that's harder to write down than to understand. What does the intermediate value theorem say? It says that if I have a function that's continuous, in some sense it's like almost the definition of continuity, but not quite, right? It says that, like, let's say I have some continuous function f, so we know that I can't make any jump, and moreover, maybe, here is A, here's another point B, then essentially I can look at f of A and f of B on the vertical axis, and I can take any point in between those two guys, and I can find some point in between A and B that realizes that value. Yeah, I think that's pretty sensible too. So why is that going to be important? Well, in particular, suppose that I have a continuous function f of x, and I give you 2 points, L and R, for left and right, in case you're, keeping track. And I have the following kind of funny property, that f of L times f of R is less than 0. What is that? This is just like kind of slick notation in a sense. Why do I care that f of L and times f of L R is less than 0? What can I conclude about those? Yeah. There's a 0 between them. In particular, f of L and f of R differ in sign, S-I-G-N. Yeah? So in this picture here, I have a function, I have a point L, a point R, and here the value of f is not the same between them, or does not have the same sign on those two sides. If you have an idea how I could, like, in some sense, as we just suggested, we know somewhere between L and R is a root. How can I refine my estimate? By the way, this picture is not great. Like the human brain really wants symmetry, and that's actually a problem for deriving these algorithms. There we go. Yeah. Pick a point halfway in between. Let's call it M for middle. All right. Well, that doesn't matter. I just want to find a root. Cool. So I think our intuition's right. So maybe we take M to be L plus R divided by 2. By the way, it doesn't have to be that point, but that feels like a pretty sensible choice. Okay, and we look at this product. Our colleague's absolutely right. We multiply those two things together. If it's negative, then what do I know? I know that somewhere between L and M is a root. Yeah. So in particular, how should my update be in this case? This is one of these like little mild brain exercises. That's right. Right, because now I know that there's a new interval between L and M where there's a root. So I should set the right to be M. And otherwise, well, we can do the opposite. Yeah. I guess there's a third case, which is just equal to 0, and then you should just stop. Yeah. Okay, so that's a very simple algorithm, I think. And we'll call this technique bisection for obvious reasons. Yes. Is there an optimal initial L and R? Well, I suppose the optimal one is when one of those two is a root. Yeah, so one question is like, well, what if I don't have L and R, right? So notice I changed my conditions ever so slightly. I said my input is F and also 2 points that differ in sign. You could ask a totally reasonable question, which is what if I don't know those 2 points? There are search strategies, but again, they're not guaranteed to be effective. If the only thing that I know is continuity, then it could easily be that I have a function that looks like the following. Like it starts over here, it goes to the bar, a little bit like that. And it would be very difficult to know where that point is. Yeah. Now, the reality is this doesn't happen too often. So I think, for example, if you know that F is monotonic, then one thing you could do is just keep moving to the right until it becomes positive or something like that. But you need some kind of property. Otherwise, you really are in trouble. Yeah. Okay, cool. So hopefully we all agree that bisection is a pretty reasonable technique. Here's a picture of what it looks like. So here we have this nice curve. We see that L and R differ. X star, by the way, is going to be our notation for the root. So basically, we look at the center point. It's positive, so we can restrict our interval to the one on the right. Okay. I told you guys, today's lecture is going to be a little easier, which I think is good. So let's say that we think about the maximum error of my root estimate. Yeah. So like at some point, this is sort of similar to eigenvalue algorithms in the sense that do we ever actually find the root in this technique? No, we bracket the root, right? We know it's somewhere between L and R, but we never actually find X star. This is going to be the property for all of the algorithms we talk about for the rest of this course, basically. It's really hard to solve numerical problems exactly, yeah? So in particular, if I return any point between L and R, like I run my code for 10 iterations, then I just stop, right? So I divide my interval in half 10 times. Then what is the maximum error? Well, one thing that we can do is we can say, okay, the error in iteration k plus 1, kind of no matter where I return the actual estimate of X star, well, we certainly know that it's less than, in the worst possible case, 1/2 the error of the last guy, right? Assuming that, like, for example, I return the whole interval for obvious reasons. I divided my interval in half, yeah? So what does this mean? This means essentially that the sort of phrase that we use a lot in numerical analysis, which I think is like hard to think about the first time around. So notice what that means is that really I have like 1/2 to the k times the initial error of my interval, right? This is, I think we can all agree on. It's tempting to say that this algorithm has exponential convergence because there's an exponent here, but that is not right. The common terminology in numerical analysis is that the next error is a linear function of the previous error. And so we call this algorithm a technique with linear convergence. Okay, so this is just the terminology to remember. This is called linear convergence, like that, which is a very common misconception. So like it looks like it's exponential, but it's not. It's linear. Um, let's say that I plotted the error. Like so I plot that exponential. There's an exponential, in case you're wondering. How should I modify this plot to check if my algorithm has linear convergence? Yeah, so if I use like sort of a log for the vertical axis, right? Notice what is the log of this expression? It's k plus 1/2. So basically, you know, if I take the log, then I'm going to get a slope, which looks like 1 over k. Yeah. So that's the way to go about that. Okay. So as we talk about our different algorithms, we should ask a few questions. One is, does this thing converge? The answer is absolutely, unconditionally, as long as my input brackets a root. If it doesn't, then I had no business using this technique to begin with. How quickly? Now we've learned a piece of terminology, which is that this algorithm converges linearly. Not exponentially, not quadratically, linearly. This is a terminology. There's no, like, this is just a choice in the literature. There's no, like, fundamental thing. Yeah. Yeah, so if it converges quadratically, which we're going to see in a moment, then this expression is going to be quadratic in EK. So notice when, like, we're concerned with small errors, right? So small things squared are even smaller. So a quadratic convergence is preferable to a linear convergence. Yeah. Assuming you have a good initial estimate, which is exactly the issue in algorithms like Newton's method. Okay. So essentially we have some set of information like this that you know, our error bound is divides by 2 every time, and that's how we got the linear convergence result. Now we're going to flip to a slightly different problem just for a moment, and we're going to show that we can get faster convergence for that problem, which is actually equivalent to root finding. That problem is going to be finding a fixed point. Okay, so let's say that I want to find, I'm given a function g, and I want to find a point x where g of x is equal to x. Yeah. Notice that this is really root finding, right? I could define f of x, whoa, is equal to g of x minus x, and this is root finding like that. So these problems are completely equivalent. But for some problems, like fixed point, it's going to feel a little bit more natural. So let's think about that for a second. Now, fixed point problems, there's sort of one algorithm staring us in the face that at least converges when you initialize it with the solution to your problem, which is probably not a great argument. In particular, here's a very simple algorithm, which is as follows. X, which is, okay, I'm trying to find a fixed point of g, so what am I going to do? Well, I know at the very least that x star, this thing leaves x alone, right? So I might ask, what happens if I just iterate this expression? I just keep putting x back into g. Is there any universe in which I get lucky and this converges to a fixed point? Let's actually draw some pictures of what this technique looks like. So let's say that I have a function. I really struggle to draw this. I'm going to apologize in advance. We're going to try. But this, spoiler alert, it's going to depend on the slope of our function, and it's hard to draw this accurately. In any event, what is this thing doing? In some sense, I'm going to draw a very particular curve. This is y equals x, like that. I'm going to draw a visualization that people usually use when they talk about fixed point iteration. So let's say that my function g looks like this. I think I managed to do it right. Okay, so what does fixed point iteration do? Well, in some sense, so let's say that like this is x0, right? Well, now I can evaluate this function here, right? So that's g of x0. And then what do? I kind of flip the x and the y axes. Do you see that? Because like this is a point where y is equal to g of x0. And now my next iterate should be a point where x is equal to g of x0. Notice that I drew the line y equals x, and that's because you can understand the next iterate of fixed point iteration as moving horizontally to y equals x and then back down. Does that make sense? Like pictorially how I got from this expression to this picture? Let's try that again. So what are we going to do? We have x we evaluate g, that gives us this point, right? And now our next x is going to be the point whose x coordinate is equal to the y coordinate of this point, right? So these are all the points whose y coordinates are equal to this guy. We want x equals y, and so that's why we go back down here. That make sense? Okay, notice a really beautiful thing happen. So our x star in this case is like here-ish, right? We got closer. That's kind of cool. In fact, what happens if I iterate again? Well, now we kind of get the pictorial thing. We go to the y equals x, we go down, and now we're like super close. So at least in this particular case, perhaps because your instructor knows how to draw the diagram strategically, notice the fixed point iteration actually converged to a fixed point, right? Like the more I step, the closer I get to this x star. Now, one might conjecture from this picture, like, oh, great, so if I have a fixed point problem, I just iterate this thing and I converge. Let's draw a picture where that doesn't happen. This is where I was watching my old course video, which if you haven't figured out, is my like lazy way of preparing for class. Here's y equals x. Now let's suppose I have a function that like grows really quickly, like that. Okay. Oops. Problem is that the slope of y equals x is already kind of big. But in any event, okay, let's say that I initialize here. So what's our picture? Well, we go up to our curve and then across to y equals x. That brings us here. Notice our actual x star is there, right? That's not so good. So now we go up to our curve again. So notice that our algorithm in this case is diverging. Okay, so fixed point iteration doesn't always work. From this picture, can we conjecture when it works and when it doesn't? What's the difference between the two curves I've drawn? Well, this g looks kind of flat, and this guy looks kind of up. Yeah. When the average slope is less than y equals x. That's almost right, but I think more generically, it's just that we're going to want the slope to be bounded above probably by 1, right? Notice, remember that we actually introduced a condition on our previous slides for like slope being bounded in a very generic fashion, which is Lipschitz, yeah? So that's a good conjecture. Let's actually check it. Notice I've basically put the conjecture I wanted in the mouth of our student in the audience. Okay, so this is one of these proofs that is important not to think too hard. So in particular, what would be kind of nice? Well, let's say that we have a fixed point x star, right? So in particular, I know g of x star is equal to x star. And now, one thing that I could do is just look at the error of the kth iteration. So that's the absolute value, because we're in one dimension so far, of xk minus x star. Yeah? Okay. So notice, by definition, a fixed point iteration, xk is the same as g of xk minus 1. And by the way, because x star rather is a fixed point, this is g of x star. Cool? All right. So our conjecture is absolutely right. Let's say that g is 1 Lipschitz, right? So, or c Lipschitz more generically. Then basically that property says, well, here, see, we have absolute value of a difference in g, that we have xk minus 1 minus x star, like that, right? Which is basically equal to c times ek minus 1. Yeah? So notice, what did we show? We showed that so long as we are c Lipschitz and c is less than 1, our algorithm converges. And what is its rate? What was that? A little louder. Linear. That's right. Oh, you killed me. Yeah, because notice that it's a linear expression in ek minus 1. Now here's a magical thing. I think that we can actually show this algorithm converges really fast in certain cases. So notice, if we look back at our picture, it kind of feels faster than linear. Do you see that on the left-hand side? Like it zipped really close to x star in basically one shot. So let's see if we can actually justify that picture. Is it okay if I erase this proof? I think this one we could all agree on. I kind of want that picture to persist. Okay. So now we're going to add some assumptions on g. I'm going to show in a certain case that we can actually justify that this algorithm converges really fast. So in particular, suppose that g is continuously differentiable. So in our fancy math words, we're going to say it's C1. Okay? And moreover, suppose that G prime of X star is equal to 0. That's not quite the case in our picture, but it's pretty close. Yeah? Okay. So in this particular case, one thing we can do is write a Taylor series for G, which is valid because it's differentiable. And we're going to write that Taylor series about X star. Notice what's going to happen to the linear term? 0. Yeah? So in particular, G of xk is going to be equal to G of X star plus, well, it's going to be G prime of X star times the difference, but that's just 0. So we can skip to the third term. 1/2 G double prime of X star times xk minus, X star squared, like that, plus something that vanishes like xk minus X star cubed. Cool? Isn't this kind of fun? Like I basically chose a point where it happens to be flat. Yeah? Okay. So now notice our Lifshitz argument that I wrote and erased kind of like, it certainly applies, but in some sense, like, we feel like we can do better because now there's only a quadratic term left, right? There's no linear thing to worry about. And that's more or less what's going to happen. So in particular, let's look at the error bound of ek. So this is the absolute value of xk minus X star. And now we have an expression. Oh, and because we're doing fixed point iteration, this is the G of xk minus 1 minus G of X star. Cool? Okay. So now we're going to plug in this Taylor series. Yes? Good question. Let's put a 2 there for now. You're right, because there's a second derivative here. Yeah, I'll go back and think about it. I believe... No, actually, I think you do need to do it. Now that I think about it. Okay, good question. Yeah, somebody remind me to fix that in the slides. Okay. So I think up to that, I think we're okay. So now let's plug in our Taylor series. Now instead of xk, we're going to have xk minus 1 because we are. Okay, so in particular, if I take notice that basically this G of X star and that G of X star are going to cancel, right? So what we're left with are just these 2 additional terms. And so using the triangle inequality, we can bound above that this is 1/2 absolute value of G double prime at X star, like that, times xk minus 1 minus X star squared. And then we have plus big O of xk minus 1 minus X star cubed. Okay? All right. So now we're going to do kind of a sneaky thing. I keep saying that. So basically, this term is kind of annoying. Notice that like this thing here is ek minus 1, right? Moreover, yeah, so we are going to need C2. So in some neighborhood, let's say an epsilon neighborhood of G double prime, or maybe not nice, some relatively small neighborhood. If I have a positive epsilon, notice that I can just sort of make sure that this number is bounded in some particular fashion, right? So in particular, like essentially G double prime as I move away, nothing too crazy is going to happen. Or in fact, actually, I don't need that now that I think about it. What I'm going to need is the following. Sorry. Let me try the last 2 sentences again. My apologies. I prepared and then got confused. Okay. Let's say that I'm very close to X star. Sorry, this is a better argument. Erase the last 2 sentences. My bad. Let's say that xk minus 1 is very, very close to X star. This number is going to be small. Do we agree? In some neighborhood, here's the sneaky thing that I can do. I can just say like, well, in some neighborhood of this thing, I can just bound this above by a constant. Yeah? So in particular, I claim that as long as X star and xk minus 1 are sufficiently close for some notion of sufficiently, I can do the following. My apologies for the previous 2 sentences, which I can write that this is equal to 1/2 G double prime of X star times, plus epsilon times xk minus 1 minus x star squared. Let's think about y. So let's say that I'm at least, I guess, 1/2 epsilon away from x star. Yeah? Then notice that basically what I've done is this is a cubed number. I've grabbed off one of the cubes, right? And I've upper bounded it by epsilon. So as long as I'm in an epsilon neighborhood, then this expression is true. I got there. I'm sorry. I wrote it in my notes, but I didn't justify it. I got myself confused. Does this bound make sense? So as long as this guy is in an epsilon neighborhood of x star, this expression holds. Cool? All right. What did I just show? Converges quadratically. Do you see that? So, well, what is this expression? This is exactly 1/2 times g double prime of x star plus epsilon times xk minus 1 minus x star squared. Cool? Oh, oops, wait, I just copied the last expression. What I meant to write was ek minus 1. I'm sorry, I'm getting tired because it's the end of lecture. So, squared. Thank you. We're almost done, I promise. This is good. I'm going to go back to sleep. I woke up at like 2 a.m. yesterday and couldn't get back to sleep. All right. So basically what do we show? We show that we upper bounded ek as a quadratic function of ek plus 1. Now we have to be the tiniest bit careful. In order to have convergence, we need this number to be small, right? And so that's basically what we need to double check. But assuming that this number is actually less than 1, then we're all set. Okay, so one thing that we can show is that essentially as long as we're very, very close to x star, we're all set, so long as maybe the second derivative is bounded below 1. Yeah.
So like how many steps does it take to have that epsilon?
Well, no. So we have to be very careful. So essentially what we showed is there exists a neighborhood around x star for which this algorithm converges, but we did not justify that it's a very small one. Yeah, absolutely. You have to be very careful with that. Yeah. Notice, by the way, that let's see here, sufficiently close to, so there's one additional thing. So there's a question which is like, how do we justify that this thing converges? So one question, so what we've shown is, if this number is less than 1, then it converges. That's a byproduct of the expression we wrote so far. I claim we can actually say something better than that, which is as follows. Recall from our previous proof, right, that when the slope, like the first derivative of our function is upper bounded by 1, then we converge. So notice g prime of x star is equal to 0. So as long as I initialize in a neighborhood where the slope is between plus or minus 1, which I know exists because it's C1, yeah, then it will converge. And then the good news is eventually it will converge quadratically when this bound kicks in. Yeah. Yes?
Would this also be generalized if you have first couple of gradient figures? So like if the first n gradient positive, then it will converge individual on this one?
Yeah, it's a reasonable question. So first of all, you have to be absolutely careful. So the place where I evaluate g prime is not at the xk. It is at the fixed point. So the first gradient and the second gradient are all the same. Yeah. So the condition for quadratic convergence has to do with the behavior at the fixed point. So I don't think what you're saying is quite right, but it's absolutely the case that essentially we have two different proofs of convergence for fixed point iteration. One says if my slope is upper bounded by 1, then I converge linearly, right? Now from that thing, what do we know? We know in some neighborhood of x star it converges linearly, right? Now, what we showed is that if we get close enough to x star, then eventually the second bound kicks in, and now we converge quadratically. Okay? So by the way, generically what that means is it converges quadratically because we only really care about asymptotics. Yeah. I saw another question, a hand, and then it went away. Yes?
What if your initialization is just terrible, such that like the first, n steps of your iteration dominate like the runtime?
Yeah, it's a good question. So if your initialization is terrible, it might diverge, might not converge. Yeah. So these algorithms rely on having a good initial estimate. Yeah.
So when you rely on a good initial estimate, like how do you sort of enforce that you've like chosen a good initial estimate?
It's a reasonable question. So in practice, implementing techniques like this is quite complicated. Anybody, I think especially in the computer graphics domain, where it's very common to implement Newton algorithms, which is where we're going with this, probably knows that it's very frustrating. So a very typical thing to do, for example, is to use this method, and if it looks like it's diverging, like the x's are flying far away, then go back to a stupider method, do a few steps of that, and then try again. But absolutely, these things get really complicated really fast. Okay, so the good news is we have shown that there are conditions under which fixed point iteration can work, and moreover that it's quadratic. So essentially what we're going to start our next lecture with, because we're out of time today, is the most famous algorithm for root finding, which is a particular technique called Newton's method. And what Newton's method is going to do is it's going to say, okay, let's say that I approximate f of x as f of xk plus f prime of xk times x minus xk, right? This is a Taylor series, right? Now I can just solve this expression for x, and what am I going to get? Well, if you think about it, I'm going to get x, if I want to find the root of this thing, so I set it equal to 0, right? Then I'm going to get that xk plus 1, if that's what I define it to be, is going to be equal to xk minus f of x divided by f prime of x, k, like that. Notice this is a fixed point iteration, right? So essentially what we're going to begin our next lecture with is double checking that this thing satisfies the conditions that we had for quadratic convergence that we just derived, and hence, if we initialize Newton's method for root finding close to a root, it converges quadratically as opposed to linearly. Okay? So that's basically our trick. Now what is Newton's method doing? It's just taking some nonlinear function, having it at a point, linearizing it, and like that's our next iterate, is finding the root of the line. Cool? All right, so we'll begin our next lecture by doing that a little bit more carefully, deriving quadratic convergence of Newton's method, then doing Newton's method in higher dimensions, and talking about a technique called Broyden, which essentially has to do with what if I don't have a derivative? I need to do some approximation using a secant.